dark matter, and dark energy. Chapter 1. The universe that shouldn't exist. For most of human history, the universe seems simple. Look up at the night sky, and what you see appears to be the entirety of existence. Stars, glowing clouds of gas, distant galaxies scattered across an immense cosmic ocean. For centuries, astronomers assumed that everything in the universe could ultimately be traced back to the matter we could observe. The luminous material that shines, reflects light, or emits energy. In this picture, the universe was built from familiar ingredients: stars, planets, dust, gas, and radiation. Gravities governed how these things moved, pulling matter together into galaxies and clusters. The rules were elegant, and for a time they seemed to work. But as telescopes improved and astronomers began measuring the motions of objects in space with greater precision, something strange started to emerge. The universe wasn't behaving the way it should. To understand why this was surprising, we need to think about how gravity works. According to the theory of gravity developed by Isaac Newton, every object with mass pulls on every other object with mass. The more mass something has, the stronger its gravitational pull. Astronomers realized they could use this principle almost like a cosmic weighing scale. By measuring how fast objects were moving, stars orbiting inside galaxies, or galaxies orbiting within clusters, they could calculate how much mass must be present to hold those systems together. If the mass was too small, gravity would be too weak, and the system would fly apart. This method worked beautifully across the solar system. The motions of planets around the sun matched gravitational predictions with remarkable accuracy. The mass of the sun explained the orbits perfectly, so astronomers assumed the same logic would apply on larger scales. But in the early 20th century, when scientists began studying the motions of entire galaxies inside galaxy clusters, the numbers refused to cooperate. One of the first people to notice this problem was the Swiss astronomer Fritz Zwicky. In the 1930s, Zwicky was studying a massive grouping of galaxies known as the Coma cluster. This cluster contains thousands of galaxies bound together by gravity, all orbiting a common center. Zwicky carefully measured how fast those galaxies were moving. What he discovered was astonishing. The galaxies were moving far too quickly. According to the amount of visible matter in the cluster, the stars and galaxies that telescopes could observe, the cluster simply did not contain enough mass to hold itself together. The gravitational pull should have been far too weak. By all known laws of physics, the galaxies should have escaped the cluster long ago, drifting apart into intergalactic space. But they hadn't. The cluster remained intact. Something invisible had to be providing additional gravitational pull. Zwicky concluded that there must be enormous amounts of unseen mass hidden within the cluster. Matter that did not emit light, did not reflect light, and could not be detected by telescopes. He called this mysterious substance dunkle Materie, dark matter. At the time, the idea was so strange that many astronomers largely ignored it. After all, the concept of an invisible substance dominating the mass of the universe seemed almost absurd. For decades, the mystery lingered quietly in the background of astrophysics. Then, many years later, the universe delivered a second and even more dramatic clue. In the 1970s, the American astronomer Vera Rubin began studying how stars move inside galaxies. To understand what she expected to see, imagine the solar system. The planets closer to the sun move faster because the sun's gravity is strongest near its center. As you move farther away, orbital speeds gradually decrease. Astronomers assumed galaxies should behave the same way. A galaxy is essentially a gigantic rotating disk made up of billions of stars. Most of the visible mass is concentrated toward the center, where the density of stars is highest. That means gravity should be strongest there, so stars near the center of a galaxy should orbit rapidly, while stars near the outer edges should move more slowly. This prediction seems straightforward, but when Rubin and her collaborators measured the actual speeds of stars in galaxies, the results made no sense. Stars at the outer edges were not slowing down. They were moving just as fast as stars near the center. In some cases, they were moving so quickly that, according to the visible mass of the galaxy, they should have been flung off into space. But they weren't. The galaxies remained stable. The only explanation was that something massive and invisible surrounded the galaxies, extending far beyond the regions where stars were visible. Instead of containing only the stars we can see, galaxies appeared to be embedded within enormous halos of hidden matter. These halos were vastly larger than the visible galaxies themselves, containing far more mass than all the stars combined. Astronomers call the graph that shows these unexpected star speeds a galaxy rotation curve. If only visible matter existed, the curve should slope downward as distance from the galactic center increases. Instead, the curve stays flat. The outer stars keep moving at high speeds, as if an enormous amount of unseen mass is holding the galaxy together. By the late 20th century, the evidence had become impossible to ignore. Observations of galaxy clusters, galaxy rotation curves, and large-scale cosmic structures all pointed toward the same conclusion. The universe contains far more mass than we can see. In fact, the visible matter, the stars, planets, gas, and dust that fill the cosmos, appears to make up only a tiny fraction of the total. Everything we observe directly may account for only a small portion of what actually exists. The rest is invisible. Astronomers now estimate that roughly 85% of all matter in the universe is dark matter, a mysterious substance that does not emit light, does not absorb light, and does not interact with ordinary matter in any obvious way. Yet its gravitational influence shapes the structure of the entire cosmos. Galaxies form within it. Galaxy clusters are held together by it. And the large-scale web of the universe, the vast cosmic structure stretching across billions of light years, appears to be sculpted by its invisible presence. In other words, the universe we see may not be the real universe at all. It may simply be the glowing surface of something far larger and far stranger. A hidden cosmic scaffold made of matter we still do not understand. Chapter 2. The invisible skeleton of the cosmos. Once astronomers accepted that something invisible must be influencing galaxies, a new question immediately emerged. If dark matter exists, where is it? Is it scattered randomly throughout space? Is it concentrated in galaxies? Or does it form structures of its own? To answer these questions, scientists began mapping the universe on its largest scales. What they discovered revealed a structure far more dramatic than anyone had imagined. Galaxies are not sprinkled randomly through space like grains of sand. Instead, they form vast interconnected patterns stretching across billions of light years. When astronomers plot the positions of millions of galaxies, the universe begins to resemble something unexpected, a gigantic cosmic web. Long filaments of galaxies stretch across space like threads. At the intersections of these threads sit enormous clusters containing thousands of galaxies. Between them, lie immense, empty regions called cosmic voids, vast expanses where very few galaxies exist at all. If you could zoom far enough out to see the universe as a whole, it might look less like a smooth cloud of galaxies and more like a three-dimensional spiderweb made of light. Astronomers call this structure the cosmic web. But this discovery raised another mystery. Why would the universe form such an intricate pattern? Gravity alone, acting only on the visible matter we see in stars and gas, cannot easily produce structures on this scale. When scientists attempted to simulate the growth of galaxies using only normal matter, the resulting universes looked completely wrong. Galaxies formed too slowly. Large structures never appeared. The simulated universe remained far smoother and more uniform than the real one. Something was missing. Then researchers began adding dark matter into their models. And suddenly, the simulations began to match reality. Because dark matter interacts strongly through gravity, but not through light, it behaves differently from ordinary matter. Soon after the birth of the universe, tiny variations in density began to grow. Regions containing slightly more matter exerted stronger gravitational pull, drawing in more material and becoming denser over time. Dark matter amplified this process dramatically. Invisible clouds of dark matter began collapsing under their own gravity, forming enormous structures known as dark matter halos. These halos became the scaffolding of the universe. Ordinary matter, gas, and dust then flowed into these gravitational wells. Over millions and billions of years, that ordinary matter cooled and condensed, eventually forming stars and galaxies. In other words, galaxies may have formed inside massive invisible cocoons of dark matter. Without those halos, galaxies might never have formed at all. This idea means that when we look up at the night sky, we are not actually seeing the full structure of the universe. What we see, the glowing galaxies, are simply the bright nodes sitting along a vast hidden framework. The real architecture of the cosmos is largely invisible. But how can scientists study something that emits no light? Surprisingly, the universe itself provides a way to reveal it. The method relies on one of the strangest predictions of modern physics, the idea that gravity can bend light. This effect comes from the theory of gravity developed by Albert Einstein. According to his theory, massive objects do not simply pull on things through space. Instead, they actually warp the fabric of space itself. Imagine placing a heavy ball on a stretched rubber sheet. The sheet bends downward around the ball. If a marble rolls nearby, its path curves because the surface beneath it is distorted. In a similar way, large masses in the universe bend the paths of passing light. When light from a distant galaxy travels across the universe and passes near a massive object, its path curves around that object. To an observer on Earth, the distant galaxy may appear slightly distorted, stretched, or even multiplied into multiple images. This phenomenon is known as gravitational lensing. Gravitational lensing has become one of the most powerful tools for detecting dark matter. Because light bends in response to gravity, astronomers can map where mass exists, even if that mass cannot be seen. By carefully measuring how light from distant galaxies is distorted, scientists can reconstruct the distribution of invisible matter lying between us and those galaxies. When they perform this analysis across large regions of the sky, an extraordinary picture emerges. Dark matter appears to form enormous halos around galaxies. Even more dramatically, it stretches across space in massive filaments, connecting galaxy clusters. These filaments trace the hidden skeleton of the cosmic web. Some of the most detailed maps of this invisible structure have been produced using space telescopes operated by the European Space Agency and the NASA. Their instruments can detect incredibly subtle distortions in the shapes of distant galaxies, revealing the gravitational fingerprints of dark matter spread across the universe. But perhaps the most striking evidence for dark matter came from an extraordinary cosmic collision. This event involved two enormous galaxy clusters smashing into each other at incredible speed. The system is known as the bullet cluster. When galaxy clusters collide, different components of the clusters behave differently. The galaxies themselves are relatively small compared to the space between them, so most galaxies simply pass by each other without direct collisions. However, the hot gas filling the clusters behaves differently. This gas makes up much of the visible mass in galaxy clusters. And when the clusters collide, the gas clouds slam together violently, heating up and slowing down. Astronomers can observe this gas using X-ray telescopes, but when the scientists mapped the mass of the system using gravitational lensing, they discovered something astonishing. The majority of the mass was not located where the gas had accumulated. Instead, it had passed straight through the collision. In other words, the visible matter, the hot gas, had slowed down and clumped together, while most of the mass continued forward, unaffected. The only explanation was that most of the cluster's mass consists of something that does not interact with ordinary matter, except through gravity. Dark matter had effectively passed through the collision, like two ghostly clouds sliding through one another. This observation became one of the clearest pieces of evidence that dark matter is real. It showed that the universe contains enormous amounts of mass that behave very differently from the matter we know. And this hidden mass is not just scattered randomly. It forms structures, massive halos surrounding galaxies, filaments stretching across billions of light years, and a gigantic cosmic network that guides the formation of galaxies and galaxy clusters. Taken together, these observations suggest something remarkable. The luminous universe we see, the stars, galaxies, and glowing clouds of gas, may only be the visible decoration on a far larger invisible structure, a hidden framework that supports the entire cosmos, an enormous gravitational architecture stretching across the universe, a vast unseen scaffold. In other words, the universe appears to be built on an invisible skeleton made of dark matter. Chapter 3. What is dark matter? By now, the evidence for dark matter is overwhelming. Galaxies rotate too quickly for their visible mass. Galaxy clusters remain bound together when they should fly apart. Gravitational lensing reveals huge amounts of invisible mass-bending light across the cosmos, and the large-scale structure of the universe, the cosmic web itself, appears to have formed around massive halos of unseen matter. All signs point toward the same conclusion. Something enormous is out there, something invisible, something that outweighs all the stars, planets, gas clouds, and galaxies we can see. Yet despite decades of study, scientists still face a humbling truth. No one knows what dark matter actually is. This is one of the greatest unsolved mysteries in modern physics. Astronomers can map dark matter's gravitational influence across billions of light years. But when it comes to identifying the particles that make it up, the answer remains frustratingly elusive. So what could dark matter be? Over the years, physicists have proposed several possible candidates, new kinds of particles that do not appear in the standard model of known matter. One of the most widely discussed ideas involves particles known as WIMPs. The name stands for weakly interacting massive particles. The concept is simple but powerful. If dark matter consists of particles that have mass, but interact only through gravity and the weak nuclear force, they would be extremely difficult to detect. They would pass through ordinary matter almost completely unnoticed. Yet, because they still possess mass, they would exert gravitational influence. Exactly what astronomers observe. WIMPs became a popular theory because many models of particle physics predicted that particles like this should exist. If they were created in large numbers during the early moments after the Big Bang, they could still be filling the universe today. In fact, if WIMPs exist, billions of them may be passing through your body every second. They would flow through the earth, through the atmosphere, and through everything around us like invisible ghosts. And we would never feel them, because their interactions with normal matter would be incredibly rare. Another intriguing possibility involves a very different kind of particle known as an axion. Axions are hypothetical particles that are incredibly light, far lighter than electrons, yet they could exist in enormous numbers throughout the universe. Unlike WIMPs, axions would behave less like individual particles and more like a subtle field permeating space. Some physicists believe that if axions exist, they could occasionally convert into tiny flashes of electromagnetic radiation when they pass through powerful magnetic fields. Experiments around the world are now searching for exactly this kind of signal. Then there are sterile neutrinos. Ordinary neutrinos are already some of the strangest particles in physics. They are produced in nuclear reactions inside stars, supernova explosions, and radioactive decay. Trillions of neutrinos pass through your body every second, yet almost none of them interact with the atoms around you. Sterile neutrinos would be even more elusive. They would interact only through gravity, not through the forces that affect normal neutrinos. If they exist, they could account for some or all of the dark matter filling the universe. But so far, none of these candidates have been confirmed, which is why scientists around the world have built increasingly sophisticated experiments designed to catch even the faintest hint of dark matter. Some of these experiments are hidden deep underground, buried beneath mountains or located in old mines. These detectors are shielded from cosmic radiation and other background noise. Their goal is to wait patiently for a dark matter particle to collide with a normal atom. An incredibly rare event that might produce a tiny flash of energy. The detectors must be extraordinarily sensitive. In some cases, scientists cool them to temperatures only a fraction of a degree above absolute zero to eliminate any possible interference. Even then, years may pass without a single confirmed detection. Other scientists search for dark matter using powerful particle accelerators. The most famous of these is the Large Hadron Collider at CERN near Geneva. Inside this enormous machine, protons are accelerated to incredible speeds and smashed together at energies similar to those that existed just after the Big Bang. If dark matter particles can be created in these collisions, scientists hope to detect them indirectly. Because dark matter would not interact with the detectors directly, it would escape the experiment unseen. But its presence might be inferred from missing energy. Energy that should be there, but mysteriously vanishes. So far, these searches have not produced definitive results. Meanwhile, space telescopes continue to scan the cosmos for signs of dark matter interactions. Some theories predict that when dark matter particles collide with one another, they might occasionally produce bursts of radiation that could be detected from space. Astronomers analyze gamma rays and other high-energy signals from regions where dark matter is expected to be especially dense, such as the centers of galaxies. But again, the results remain inconclusive. The mystery persists. Part of the difficulty lies in the very nature of dark matter itself. Unlike ordinary matter, dark matter does not emit light. It does not absorb light. It does not scatter light. In fact, it barely interacts with normal matter at all. If you were somehow able to see dark matter directly, the universe might appear almost completely different. Invisible clouds of it would surround every galaxy. Massive halos would extend far beyond the visible edges of galaxies, and enormous filaments of dark matter would stretch across the universe, connecting galaxy clusters in a vast gravitational network. Yet none of it would glow. None of it would shine. It would be completely dark. And the only reason we know it exists is because of gravity. Gravity reveals where the mass is hiding. Still, some scientists have begun to wonder whether we might be thinking about the problem in the wrong way. What if dark matter is not a new particle at all? What if the real issue lies in our understanding of gravity? Some alternative theories propose that gravity behaves differently on extremely large cosmic scales. In these models, the strange motions of galaxies might not require unseen matter. They could instead reflect subtle modifications to the laws of gravity themselves. These ideas, known as modified gravity theories, remain controversial. While they can explain certain observations, they struggle to account for others, especially the gravitational lensing patterns seen across the cosmic web. Another possibility is even stranger. Some researchers have suggested that dark matter might consist of enormous numbers of tiny primordial black holes. Black holes formed in the earliest moments after the Big Bang. These objects would emit little or no light, yet they would still exert powerful gravitational pull. If they were scattered throughout the universe in vast numbers, they could potentially account for some of the missing mass astronomers observe. But again, evidence for this idea remains uncertain, which brings us back to the central mystery. After nearly a century of investigation, scientists have accumulated overwhelming evidence that dark matter exists. It shapes galaxies. It binds galaxy clusters together. It forms the cosmic web, and it appears to make up most of the matter in the universe. Yet the fundamental question remains unanswered. What is it, somewhere in the universe, perhaps all around us? Vast quantities of unseen matter are quietly shaping the structure of reality. Particles may be streaming through your body at this very moment, passing through atoms, through the Earth, through entire planets without leaving any trace. And despite decades of searching with the most sensitive instruments humanity has ever built, dark matter has never been directly detected. Chapter 4. Dark Energy, the even bigger mystery. By the end of the 20th century, astronomers had already come to a shocking realization. Most of the universe was invisible. Dark matter appeared to dominate galaxies, shaping the cosmic web and providing the gravitational framework that holds large structures together. Everywhere scientists looked, the same conclusion appeared again and again. The visible universe, the stars, planets, gas clouds, and galaxies we can observe, represented only a small fraction of all the matter that actually exists. It was a profound discovery, but an even bigger surprise was waiting. To understand it, we need to step back and think about the expansion of the universe. In 1929, the American astronomer Edwin Hubble made one of the most important discoveries in the history of science. By studying distant galaxies, he found that the universe itself is expanding. Galaxies are moving away from one another. The farther away a galaxy is, the faster it appears to be receding from us. This observation revealed that space itself is stretching. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they are traveling across the surface, but because the surface itself is expanding. That is essentially what is happening in our universe. Space is growing. And because space is expanding, galaxies appear to drift apart over time. For decades, astronomers assumed they understood how this expansion should behave. Gravity pulls matter together. Every galaxy attracts every other galaxy. Over enormous spans of time, that gravitational pull should gradually slow the expansion of the universe. It might not stop the expansion entirely. That would depend on how much mass exists in the cosmos. But gravity should at least act as a kind of cosmic brake. The expansion should be decelerating. This assumption seemed so reasonable that few scientists questioned it. But in the late 1990s, two independent teams of astronomers decided to measure the expansion of the universe more precisely than ever before. They did this using a special type of stellar explosion known as a Type 1a supernova. These explosions occur when certain kinds of stars reach a critical mass and detonate with extraordinary brightness. Because these supernovae produce nearly the same amount of light each time they occur, astronomers can use them as cosmic distance markers. By comparing how bright a supernova appears from Earth with how bright it should be, scientists can determine how far away it is. And by measuring how much the light from that supernova has been stretched by cosmic expansion, they can calculate how fast the universe was expanding when the explosion occurred. This method allowed astronomers to look back billions of years into cosmic history. The two teams conducting this research were the Supernova Cosmology Project and the High Z Supernova Search Team. Their goal was straightforward. They wanted to measure whether the expansion of the universe had slowed down over time. But when the results came in, they were stunned. The universe was not slowing down. It was speeding up. Distant supernovae appeared dimmer, and therefore farther away than expected. The only explanation was that the expansion of the universe had accelerated over billions of years. Something was pushing galaxies apart, not just resisting gravity, but overpowering it. The discovery was so surprising that many scientists initially assumed there must be a mistake in the data. But repeated observations confirmed the same result. The expansion of the universe is accelerating. In other words, space itself is stretching faster and faster as time passes. To explain this astonishing phenomenon, physicists introduced a new concept. They called it dark energy. If dark matter represents invisible mass pulling the universe together through gravity, dark energy appears to do the opposite. It pushes space apart. Dark energy seems to act like a kind of cosmic repulsion embedded within the fabric of the universe itself. Today, astronomers believe dark energy makes up the largest component of the cosmos. Roughly 68% of the universe may consist of this mysterious force. But what exactly is it? No one knows. One possible explanation involves something known as vacuum energy. Even what we call empty space is not truly empty. According to quantum physics, space is filled with tiny fluctuations of energy that constantly appear and disappear. Particles briefly flicker into existence and vanish again. Some physicists believe that these microscopic fluctuations might generate a small but persistent energy throughout space. If this vacuum energy exists on cosmic scales, it could cause space itself to expand more rapidly over time. In essence, empty space might contain its own built-in energy source. Another explanation traces back to an idea proposed more than a century ago by Albert Einstein. When Einstein first developed his theory of gravity, he believed the universe was static and unchanging. But his equations naturally predicted that gravity would cause the universe to either collapse or expand. To prevent this, Einstein added a term to his equations known as the cosmological constant. This constant represented a repulsive force that could balance gravity and keep the universe stable. Later, when it became clear that the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest mistake. Decades later, the discovery that the universe is accelerating brought an old idea back into focus. What if Albert Einstein's cosmological constant was not a mistake after all? Perhaps space itself contains energy that pushes the universe apart. Some physicists think dark energy may simply be this built-in energy of empty space. Others believe it could be an entirely new force of nature acting across the cosmos. Whatever the answer, the implications are staggering. When scientists add up everything in the universe, ordinary matter, stars, planets, gas, and dust, makes up only about 5% of reality. Dark matter accounts for roughly 27%, and dark energy dominates the rest, around 68%. In other words, almost everything in the universe is invisible and still unknown. The cosmos we see is only a thin layer of a far deeper and far stranger reality.